Five Great Unsolved Problems. Number 5. Paradox of the heap. Also known as the Sorites paradox, the paradox of the heap is a paradox that arises from vague predicates. The paradox of the heap is an example of this paradox, which arises when one considers a heap of sand, or a haystack, from which grains are individually removed. Is it still a heap when only one grain remains? The problem is essentially one of philosophy of language, wherein terms may be relative and indefined, as opposed to problems in mathematics, wherein all terms by nature have some definition, even if it is only as a variable. Here is an example of the paradox in action. Premise 1. A heap of sand is comprised of a large collection of grains. Premise 2. A heap of sand minus one grain is still a heap. Repeated applications of premise 2, each time starting with one less number of grains, eventually forces one to accept the conclusion that a heap may be composed of just one grain of sand. On the face of it, there are some ways to avoid this conclusion. One may object to the first premise by denying that a large collection of grains makes a heap, or more generally, by denying that there are heaps. One may object to the second premise by stating that it is not true for all collections of grains that removing one grain from it still makes a heap. Or one may accept the conclusion by insisting that a heap of sand can be composed of just one grain. The paradox is tricky for philosophers because they must explain why one of the two premises, or the conclusion, is wrong even though they appear to be self-evident. Number 4. Do black holes exist? Do black holes really exist? Do they radiate, as expected on theoretical grounds? Does this radiation contain information about their inner structure, as suggested by gauge gravity duality, or not, as implied by Hawking's original calculation? If not, and black holes can evaporate away, what happens to the information stored in it? Quantum mechanics does not allow information to be destroyed, or does the radiation stop at some point leaving black hole remnants? Is there another way to probe their internal structure somehow? If such a structure even exists. While general relativity describes a black hole as a region of empty space with a point-like singularity at the center and an event horizon at the outer edge, the description changes when the effects of quantum mechanics are taken into account. Rather than holding captured matter forever, black holes may slowly leak a form of thermal energy called Hawking radiation. However, the final, correct description of black holes, requiring a theory of quantum gravity, is unknown. Number 3. Untriceptium. The name untriceptium is used as a placeholder, as in scientific articles about the search for element 137. Transuranic elements, those beyond uranium, are, except for microscopic quantities and except for plutonium, always artificially produced, and usually end up being named for a scientist or the location of a laboratory that does work in atomic physics. Because the significance of element 137 was first pointed out by the physicist Richard Feynman, element 137 is sometimes informally called Feynmanium, symbol Phi. Any element with an atomic number of greater than 137 would require one's electrons to be traveling faster than the speed of light. Since the early 1900s, physicists have thought that this number, 137, might be at the heart of a GUT, or grand unified theory, which could relate the theories of electromagnetism, quantum mechanics, and most especially gravity. However, physicists have yet to find any link between the number 137 and any other physical law in the universe. It was expected that such an important equation would generate an important number, like 1 or pi, but this was not the case. The question here is, what are the chemical consequences of having an element with an atomic number above 137, whose one's electrons must travel faster than the speed of light? Is Feynmanium the last chemical element that can physically exist? Number 2. Why do we dream? The events of dreams are often impossible, or unlikely to occur, in physical reality, They are also outside the control of the dreamer. The exception to this is known as lucid dreaming, in which dreamers realize that they are dreaming, and are sometimes capable of changing their dream environment and controlling various aspects of the dream. The dream environment is often much more realistic in a lucid dream, and the sense is heightened. There is no universally agreed upon biological definition of dreaming. General observation shows that dreams are strongly associated with REM sleep. REM sleep is the state of sleep in which brain activity is most like wakefulness, which is why many researchers believe this is when dreams are strongest. Although it could also mean that this is a state from which dreams are most easily remembered. During the typical lifespan, a human spends a total of about 6 years dreaming, which is about 2 hours each night. It is unknown where in the brain dreams originate, if there is such a single location, or why dreams occur at all. Number 1. What are the chemical origins of life? What are the chemical origins of life? How did non-living chemical compounds generate self-replicating, complex life forms? In the natural sciences, abiogenesis, the question of the origin of life, is the study of how life on Earth might have emerged from non-life. Scientific consensus is that abiogenesis occurred sometime between 4.4 billion years ago, when water vapor first liquefied, and 2.7 billion years ago, when the ratio of stable isotopes of carbon, iron, and sulfur points to a biogenic origin of minerals and sediments, and molecular biomarkers indicate photosynthesis. There is no truly standard model of the origin of life. But most currently accepted models build in one way or another upon a number of discoveries about the origin of molecular and cellular components for life. As of 2007, no one has yet synthesized a protocell using basic components which would have the necessary properties of life, the so-called bottom-up approach. Without such a proof of principle, explanations have tended to be short on specifics. However, some researchers are working in this field, notably Steen Rasmussen at Los Alamos National Laboratory and Jack Shostak at Harvard University.